For decades, Japanese engines were considered the gold standard of reliability. Today, some are failing before reaching 100,000 miles, leaving owners with repair bills that can exceed $10,000. Across the industry, millions of vehicles have been caught up in engine-related recalls, investigations, or widespread reliability concerns. This isn't a case of one defective model or one bad manufacturer. It's the result of a series of engineering decisions made over the last 15 years as automakers chased more power, higher fuel economy, and stricter emissions from smaller, more complex engines. So, what went wrong? These are the 10 engineering choices that are quietly changing the lifespan of modern engines. Number 10, longer oil change intervals are quietly wearing out. Modern engines. For decades, changing engine oil every 3,000 to 5,000 miles was considered cheap insurance against wear. Today, many manufacturers recommend intervals of 10,000 miles, and some even stretch them to 15,000 or 16,000 miles when full synthetic oil is used. On paper, that sounds reasonable, because modern synthetic lubricants resist oxidation better and maintain their viscosity at temperatures above 250 degrees Fahrenheit, 120 degrees Celsius. But while the oil has improved, the engines using it have become far more demanding than the naturally aspirated engines that earned Japanese brands their legendary reputation. A modern turbocharged direct injection engine operates under much harsher conditions. Turbochargers can spin at over 180,000 revolutions per minute, while exhaust temperatures often exceed 1,600 degrees Fahrenheit, 870 degrees Celsius, during heavy acceleration. That heat is transferred directly into the engine oil, which also lubricates variable valve timing systems, timing chain tensioners, and turbocharger bearings. Now add the reality of daily driving in America, short commutes, stop-and-go traffic, and frequent cold starts. In these conditions, moisture and unburned fuel contaminate the oil faster than many owners realize. The dashboard may still display 40% oil life remaining, but the lubricant can already be losing the protective film that keeps metal components separated. Here's the detail many drivers never hear. Most oil life monitors don't actually test the oil. Instead, they estimate its condition using algorithms based on engine speed, coolant temperature, mileage, idle time, and driving patterns. They cannot measure fuel dilution, microscopic metal particles, or sludge forming inside narrow oil passages. That's why many independent mechanics recommend changing the oil at 5,000 to 7,500 miles, especially on turbocharged engines, even if the manufacturer allows much longer intervals. Following the dashboard alone may save one oil change today, but over 100,000 miles, it can significantly increase wear on bearings, timing components, and turbochargers. And that brings us to another technology designed to improve fuel economy. One that actually shuts part of your engine off while you're driving. Number 9, cylinder deactivation. Saving fuel by sacrificing simplicity. On paper, cylinder deactivation sounds like one of the smartest ideas ever introduced into modern engines. If you're cruising down the highway and don't need all the engine's power, why keep every cylinder firing? By shutting down 2, 4, or even 6 cylinders during light load driving, manufacturers can reduce pumping losses and improve fuel economy by 5% to 10% under ideal conditions. It helped automakers meet increasingly strict emissions and fuel economy regulations without sacrificing horsepower, which is why the technology became common on V6 and V8 engines over the past decade. The problem is that turning cylinders on and off thousands of times during a normal drive adds an entirely new layer of mechanical complexity. Hydraulic lifters, locking pins, oil control solenoids, and electronic actuators must operate flawlessly every time the system switches modes. These components depend on clean oil and precise oil pressure to function correctly. As engines accumulate mileage, even slight oil contamination or varnish buildup can slow these mechanisms, causing rough operation, ticking noises, misfires, or lifter failures. Independent repair shops have reported that replacing failed lifters and camshaft components on some cylinder deactivation systems can cost anywhere from $2,500 to more than $6,000, depending on the engine. Japanese engineers have long believed that durability comes from reducing unnecessary complexity wherever possible. Every additional actuator, solenoid, or hydraulic mechanism introduces another potential failure point over hundreds of thousands of miles. While cylinder deactivation can deliver measurable fuel savings during standardized laboratory testing, those savings often become less noticeable in real-world city driving, where the system frequently switches between active and inactive modes. In other words, engineers gained a few percentage points in efficiency, but introduced a system that demands far greater precision throughout the engine's life. And if cylinder deactivation increased mechanical complexity, the next innovation pushed engine stress to an entirely different level. Manufacturers discovered they could replace large six-cylinder engines with much smaller turbocharged four-cylinders, producing the same power while burning less fuel. It sounded like the perfect engineering solution. In reality, it created a new set of challenges that many modern engines are still struggling to overcome. Number 8. Smaller turbocharged engines are producing big power at a big cost. 20 years ago, if you wanted 300 horsepower, you usually bought a 3.5 or 4.0 liter V6. Today, many manufacturers achieve the same output from a 2.0 liter turbocharged four-cylinder. On paper, it's an engineering masterpiece. A smaller engine weighs less, burns less fuel during standardized testing, and emits fewer greenhouse gases. That's exactly why downsized turbocharged engines have become the industry standard. But there's one fact that often gets overlooked. A smaller engine has to work much harder to produce the same performance as a larger one. Think of it like asking a marathon runner and a sprinter to carry the same weight up a mountain. Both might reach the top, but the smaller athlete has to push much closer to their physical limit. The same principle applies inside a modern engine. Turbochargers compress incoming air to increase combustion pressure, allowing a small engine to generate the power once reserved for much larger engines. During heavy acceleration, many turbochargers spin at 180,000 to 220,000 revolutions per minute, while combustion pressures inside the cylinders can exceed 150 bar, placing enormous stress on pistons, connecting rods, crankshaft bearings, and head gaskets. These engines are incredibly capable, but they operate with much smaller engineering margins than the naturally aspirated engines that made Japanese reliability famous. Heat becomes the biggest enemy. Exhaust gas temperatures under full load can climb above 1,700 degrees Fahrenheit, 925 degrees Celsius, and although advanced cooling systems keep the engine under control, that thermal energy still affects the oil, turbocharger bearings, and surrounding components. To reduce friction and improve fuel economy, manufacturers now commonly specify ultra-thin oils such as 0W20, 0W16, and in some markets, even 0W8. These lubricants improve efficiency, but they also demand extremely tight machining tolerances and consistent maintenance. Miss an oil change, ignore low oil levels, or repeatedly shut the engine off immediately after heavy driving, and the turbocharger, one of the hardest working components on the vehicle, can begin wearing far earlier than expected. Japanese engineers don't argue that turbocharging is a bad technology. In fact, companies like Toyota, Honda, and Nissan have built some exceptionally durable turbocharged engines. The concern is that modern engines are being asked to deliver sports car performance, luxury car refinement, and economy car fuel consumption simultaneously. Achieving all three means every component operates closer to its design limits. When maintenance is delayed or real-world driving differs from laboratory test conditions, those smaller safety margins become much more noticeable. And while turbocharging transformed performance, another innovation quietly introduced a completely different problem, one that develops slowly, remains hidden for years, and can steal horsepower without the driver realizing it. Number 7, direct fuel injection solved one problem, but created another. When gasoline direct injection first appeared in mainstream vehicles, it was hailed as one of the biggest breakthroughs in engine technology. Instead of spraying fuel into the intake ports, engineers began injecting gasoline directly into the combustion chamber at pressures that now exceed 3,000 pounds per square inch, over 200 bars, in many modern engines. The result was impressive. Fuel could be metered with incredible precision, combustion became more efficient, power increased, and emissions dropped. It's one of the key reasons a modern 2.0-liter engine can produce the same horsepower that once required a much larger V6. But every engineering breakthrough comes with a compromise. Older port-injected engines had an unexpected advantage. Every time fuel passed through the intake ports, it naturally washed the intake valves, removing oil residue before it could harden into carbon deposits. Direct injection eliminated that cleaning effect entirely. Meanwhile, modern engines still route oil vapors from the crankcase back into the intake through the positive crankcase ventilation (PCV) system to meet emissions regulations. Over 50,000 to 100,000 miles, those vapors can bake onto the hot intake valves, gradually forming thick carbon deposits that restrict airflow. The process is slow enough that most drivers never notice it until idle quality deteriorates, fuel economy drops, or the engine begins to misfire. Independent repair shops across North America now perform thousands of intake valve cleanings every year, particularly on turbocharged direct injection engines. In severe cases, carbon buildup can reduce airflow enough to affect power output and trigger check engine lights. The most common repair is walnut shell blasting, a specialized cleaning process that often costs between $400 and $1,200, depending on the engine design. To address the issue, some Japanese manufacturers adopted a dual injection strategy, combining both port injection and direct injection, allowing the port injectors to periodically clean the intake valves while still benefiting from the efficiency of direct injection. It's an elegant solution, but it also increases manufacturing complexity and cost. This perfectly illustrates the challenge facing modern engineers. Every new technology solves one problem while introducing another that didn't exist before. Direct injection delivered better performance and lower emissions, but it also created a maintenance concern that older engines rarely experienced. And just when manufacturers believed they had optimized combustion, they faced another obstacle. One caused not by fuel or airflow, but by something drivers rarely think about until it's too late: extreme engine temperatures. Number 6, modern engines run hotter than ever, and heat is their silent enemy. If there is one factor that quietly shortens the life of almost every modern engine, it's heat. To improve fuel economy and reduce emissions, manufacturers deliberately run today's engines at higher operating temperatures than those built 2 or 3 decades ago. A typical modern gasoline engine operates with coolant temperatures of around 200 degrees Fahrenheit to 230 degrees Fahrenheit, 93 degrees Celsius to 110 degrees Celsius, while temperatures inside the combustion chamber can exceed 4,000 degrees Fahrenheit, 2,200 degrees Celsius, during ignition. Turbocharged engines face even greater thermal stress, with exhaust gas temperatures approaching 1,700 degrees Fahrenheit, 925 degrees Celsius, under heavy load. Those numbers are a testament to modern engineering, but they also leave very little room for error. Every component inside the engine expands and contracts as temperatures rise and fall. Pistons, cylinder heads, valves, bearings, and gaskets are all designed to operate within extremely tight tolerances, often measured in hundredths of a millimeter. When everything is working perfectly, the system is remarkably efficient. But if the cooling system begins to struggle, whether because of a partially clogged radiator, a failing water pump, degraded coolant, or a thermostat that's no longer opening correctly, those tiny tolerances can disappear surprisingly quickly. A temperature increase of just a few degrees may not trigger a warning light, but over thousands of miles, it can accelerate wear on seals, weaken head gaskets, and shorten the life of plastic cooling components. Heat also affects something drivers rarely think about: the engine oil itself. As oil repeatedly absorbs extreme temperatures, its additives gradually break down, reducing its ability to protect metal surfaces from friction. In turbocharged engines, the oil doesn't just lubricate the crankshaft and camshafts, it also cools and lubricates turbocharger bearings spinning at nearly 200,000 revolutions per minute. If oil quality deteriorates or flow becomes restricted, those bearings can wear rapidly, sometimes leading to costly turbocharger failures. That's one reason experienced technicians often recommend allowing a hard-worked turbocharged engine to idle briefly before shutting it off, giving oil and coolant time to carry excess heat away from the turbocharger. Japanese engineers often describe heat as the invisible enemy of durability because it rarely causes immediate failure. Instead, it slowly accelerates the aging of nearly every component inside the engine. Rubber seals become brittle, plastic connectors harden, cooling hoses lose flexibility, and electronic sensors endure years of relentless thermal cycling. None of these changes happen overnight, but together they help explain why some modern engines become increasingly expensive to maintain as mileage climbs. And while heat affects every engine, the next issue begins long before the first mile is driven. It starts at the design stage, where manufacturers are under constant pressure to make engines lighter than ever before. Number 5. Lighter engines improve efficiency, but they leave less room for error. Reducing vehicle weight has become one of the biggest priorities in modern automotive engineering. According to the U.S. Environmental Protection Agency, cutting just 10% of a vehicle's weight can improve fuel economy by roughly 6% to 8%, depending on the vehicle and driving conditions. That may not sound dramatic, but when manufacturers are trying to meet increasingly strict emissions and fuel economy standards, every pound matters. This is why many modern Japanese engines now use aluminum blocks, thinner cylinder walls, lightweight pistons, low-tension piston rings, plastic intake manifolds, and composite cooling components. Together, these changes can remove 50 to 100 pounds from an engine and significantly improve efficiency. The downside is that lightweight engineering often leaves far less mechanical reserve than older designs. Legendary Japanese engines from the 1990s and early 2000s were frequently built with thick cast iron blocks, generously sized bearings, and components engineered with substantial safety margins. They were heavier and less efficient, but they could tolerate poor maintenance, overheating, or inconsistent oil changes far better than many modern engines. Today's designs are optimized with computer simulations that remove every unnecessary gram of material. The result is an engine that performs exceptionally well under normal conditions, but one that may be far less forgiving when something goes wrong. A single overheating event, prolonged oil starvation, or repeated heavy towing can have consequences that older engines might have survived. Weight reduction has also transformed engine internals. Low tension piston rings reduce friction and improve fuel economy, yet they rely on perfectly clean oil and precisely machined cylinder walls to maintain an effective seal. Likewise, thinner bearings reduce internal resistance but have less capacity to absorb contamination or lubrication problems. None of this means modern engines are poorly engineered. It means they're engineered for maximum efficiency within much tighter tolerances. Japanese engineers often emphasize that today's engines are designed to deliver outstanding performance and lower emissions, but they also require owners to follow maintenance schedules more carefully than ever before. That philosophy marks a major shift in automotive engineering. The old approach prioritized durability above almost everything else. The modern approach demands a balance between performance, emissions, fuel economy, weight, manufacturing cost, and reliability. It's a far more difficult equation to solve, and every compromise influences long-term durability. But perhaps the biggest compromise of all isn't made inside the engine. It's made inside the factory, where manufacturers face relentless pressure to reduce production costs while building millions of engines every year.